Hello there. This is David Williams from the Electronic Engineering Technology Department at Okanagan College, and this short video is about half-wave rectifiers. Now, a half-wave rectifier is a fairly simple circuit that takes an AC source and effectively turns it into a DC source. Now, one thing that you need to remember here as I'm going through this description is that DC simply means that the current is always in one direction, but it can still be a changing value. So what we have here is a simple circuit with an AC source, a diode, which is what's doing the rectification, and so oftentimes diodes are called rectifiers, and that's one of the main purposes of diodes, is to rectify signals or to convert it from AC to DC, and a load of some kind. And you can see over here we've got an oscilloscope that's connected to the voltage source, as well as an oscilloscope that's connected to the load. And you can see here we have the AC signal on the left-hand side connected to the source, and over here it's a DC signal across the load. It's a changing voltage across the load, and therefore changing current. But you'll see that it never goes below zero, so that current is always in one direction. Now, to really see what's going on here, I think it's going to be a little bit more instructive to take this and show that on the same scale, on the same graph. And we don't really care about what the actual magnitudes and what the actual time scale is. So I'm just going to draw here's my voltage and here's my time. If we're looking at the positive cycle, what's going to happen is this diode will become forward biased when the input voltage is above the forward voltage of this diode. So let's say that the forward voltage of this diode is 0.7 volts. So once the input voltage is above 0.7 volts, this diode becomes forward biased and current will go through it, and therefore current will go through the load, so we'll have some kind of voltage across the load. And the voltage across the load will be the input voltage minus the forward voltage of the diode. So here's what the output's going to look like on the positive cycle. At this point in time here, that's when the diode here becomes forward biased, and the output will then follow the input but be about 0.7 volts left, or whatever that, less than the input. So because of the forward bias voltage across the diode. Now when the input signal goes negative, that diode is reverse biased, no current's going through the load, therefore we will have no voltage across the load. And then the input again becomes positive over here, and as soon as the diode becomes forward biased, there will be current through the load. We will have Vin minus about 0.7 volts will be applied across the load, and this will just carry on forever. And so we're going to have output signal about 0.7 volts less than the input signal. A couple of quick pieces of information about the input and output signals. Well, the frequency of the output signal is going to be equal to the frequency of the input signal. They look quite a bit different, but they repeat themselves they've got the same period, and therefore they've got the same frequency. The average, or the DC voltage, of this output signal is equal to the peak value of the output signal over pi. The RMS value of the output signal is equal to the peak value of the output signal over 2. And of course the voltage of the output signal is going to be equal to whatever the voltage of the input signal is minus the forward voltage of the diode. So hopefully you learned a little bit in this video about half-wave rectifiers.
Let's solve a few worked examples related to our half-wave and full-wave rectifiers from our lecture. In this circuit here, we have a half-wave rectifier which converts a 15-volt peak sinusoidal AC input, or a 15-volt amplitude AC input, into a DC power supply. Here, I'm going to assume for the purposes of this worked example that we have a pretty standard silicon diode figure of about 650 millivolts for our forward voltage on that diode. In something like an exam, you'd expect to be told a little bit more about this diode, but just looking at the circuit, we can go ahead and take a simple approximation to make some assumptions about this particular diode. It really doesn't change the way the problem flows all that much if we have a different forward voltage. So I'm going to go ahead and assume 650 millivolts. We're also assuming that the load connected to this power supply is a resistive load with a minimum impedance of 220 ohms. That means the lowest impedance this is ever going to have is 220 ohms. And we can effectively use that minimum impedance to determine what the maximum current we can expect that load to draw is at a given voltage. Now, you might wonder why I give you a minimum impedance here. Why not tell you for sure this is a resistive load with a fixed impedance? Doesn't resistive load, you ask, imply that this value is going to stay relatively constant? And actually, there are quite a few different types of resistive loads whose values change over time. So take as an example a light bulb, which is made of a resistive material, behaves like a nice resistor, but whose resistance changes as it first heats up. So if I take a light bulb, connect it, I'm going to expect it to have a low resistance as it first starts to emit light. I'm going to expect it to have a relatively low resistance when it hasn't heated up at all, and then as it starts to emit light and get hot, I'm actually going to expect its resistance to increase. And so actually as the resistance increases, it starts drawing less current and potentially actually dissipates less power because its resistance has gone down. So we actually expect for a light bulb for there to be this initial startup period where we're not just putting energy into the light that we shoot out, we're also putting energy into heating up that material and effectively getting it hot enough to glow. So it's quite possible to have something that acts both resistive and which has an impedance that changes with respect to time. That's kind of an aside for this problem, but in this case we can assume that we have something that is going to have an impedance that is 220 ohms or greater, and we want to develop a worst case estimation for our supply ripple. And there are a few ways we could do this problem. We could really go crazy with this because we effectively need two pieces of information in order to solve this problem. We need to know the length of time which our supply capacitor discharges, which if we remember, this circuit, first time it charges up, then discharges, then charges up, then discharges. So it spends most of its time discharging, but it does spend a little bit of time charging there, and so by figuring out that discharge time, we could really figure out how low that voltage is going before it starts coming back up. And we need to know effectively how much current the load draws at any given voltage. So as that voltage decreases across this load, if we're assuming this is a resistive load, then the load's going to draw less current because less voltage gives us less current through a given resistance. And so we could spend the time figuring out both of these. We could actually, if we wanted to, really do some really detailed analysis and figure out the portion of the time that this capacitor is going to be discharging, and we could actually then apply our knowledge of RC circuits to try to figure out the actual discharge characteristic of this resistor. But remember, really what we want here is a worst case estimation. So there's a few things that we could do to actually make this calculation a lot simpler for ourselves. And we'll find that if we choose the right approximations, if we choose our approximations carefully, they'll also make our design a little bit stronger because they'll actually be kind of pessimistic optimizations. They'll increase our supply ripple estimation rather than decreasing that. And so when we go and actually work with the real circuit, we'll be pleasantly surprised to find out that we actually have less ripple than our pessimistic approximation led us to believe. So here we have just this little circuit here, and we're remembering that we're going to look for what the supply ripple is. So first of all, we know that the absolute maximum value that this is going to charge to is going to be equal to 15 volts, which was V in, minus the forward voltage. So we said the maximum output of this rectifier was equal to V in minus the forward voltage. So the maximum V in, that's right, this is V in max minus our forward voltage. So we can compute that. We said we were going to have 15 volts as our maximum AC input, and we said that our forward voltage was going to be 650 millivolts. So that says that Vmax, the maximum output of that rectifier, was going to be equal to 14.350 volts. So given that, we can actually try to figure out what a worst case current through that load is going to be. So remember, the current through that load is going to be highest when we have that voltage of 14.35 volts on that. Now, as the capacitor discharges, the voltage will theoretically dwindle and the current will actually decrease. But since we're trying to come up with an approximation, an estimate, and we want kind of a worst case estimate, we're actually going to make our lives easier by assuming that that current delivered to the load, the current that is coming from the capacitor, that discharge current, is constant. So let's solve for the maximum discharge current, which we know is determined by the voltage across that resistive load and its impedance. So we know that V equals IR, I equals V over R. Right? These are all just from the definition of impedance. And so I equals our maximum voltage over, now in this case the impedance is in the denominator. If we're trying to get a maximum current estimation, then we're going to want to use the impedance that gives us the most current. And since that's in the denominator, we know that we're going to use the smallest possible impedance. And I said the smallest possible impedance we could have was 220 ohms. So we can actually go ahead and plug in 14.35 volts divided by 220 ohms. And we'll find that that gives us a maximum current of 65.23 milliamps. So this is the figure that we're going to use as Imax. And the figure that we're going to use to figure out the rate at which that capacitor is going to discharge in our approximation here. So let's switch to a different color to indicate a different train of thought. Next, we want to figure out for how long that capacitor is discharging. Now, we could say that that capacitor is only going to discharge for a small percentage of that cycle, but in order to figure out what percentage of that cycle we were actually discharging for, we need to figure out how the voltage of that capacitor drops, and we get into a situation where we're creating a very complex mathematical relationship that we're going to have to deal with. And while it's not unreasonable to have to solve those kinds of equations when you want to be very precise, when you actually want to really get into a detailed description of the circuit, we're looking for a worst case estimate. So what we're actually going to do to make our lives easier is we're going to assume that the capacitor effectively charges instantaneously and thus spends the whole cycle discharging. And so again, because we're actually increasing our discharge time, we're increasing our worst case estimate. So we're losing a little bit of accuracy in our estimate, but we are, again, going to be pleasantly surprised when we actually go to our real circuit and find that it works a little bit better than our specifications. So let's continue here, and we'll see that we have a 60 hertz signal, which means that a single cycle of that 60 hertz signal, while our frequency is equal to 1 over our period, so if we do the math out, we'll find that the period of this signal is actually 16 2/3 milliseconds per cycle. And so now we know effectively a single cycle of this AC input is going to be 16 2/3 milliseconds long. So in our approximation, we're going to say that the capacitor's discharge time is approximately equal to 16 2/3 milliseconds. In reality, it'll actually be discharging for a little bit less time, but that just makes our estimate a little bit safer. So that's acceptable for our approximation. All right, so we figured out the time. So I'm going to write this as delta T as our discharge time equals 16 2/3, or 16, I'll approximate that as 16.67 milliseconds per cycle. And interestingly, you're going to see this number of 60 hertz quite frequently. And that's not because 60 hertz is some kind of fundamental constant of the universe, but rather because 60 hertz is the frequency that we've chosen for the wall voltage in the United States. So I'm assuming that most of my viewing audience is typically in the United States, where the wall voltage is 60 hertz, and the number 60 hertz is going to come up a lot. In Europe and in other countries, the actual wall frequency varies. Sometimes it's 50 hertz instead of 60 hertz, which can have some significant impacts on these kind of circuits. But for our purposes, we're going to see that number 60 hertz a lot in this class. Okay, and so let's take these two trains of thought and see if we can use them to figure out what the maximum supply ripple is going to be. And so if we remember our very basic description of the capacitor, we said that capacitor current occurs when we have a change in voltage. And the amount of current that was going to occur for a given change in voltage depended on the physical ability of the capacitor to store charge, or its capacitance. And so he kind of said that our fundamental capacitor relationship was that I, or current, was equal to the capacitance of that capacitor times the change in voltage, right, with respect to time. And if we want to, we could rewrite this for an average amount of current by saying that an average current is going to equal to, the average current through this capacitor is going to equal to its capacitance times the change in voltage over the change in time. So we've gone from our instantaneous current here to our average current, but for our purposes, we're assuming that that current is constant, so the average current should equal the actual current. So in our assumption, it's perfectly valid to use this simplified formula here. And so given that, we actually have everything we would need to figure out what the supply ripple, or change in voltage, is for a given period of time, or for a given discharge period. So let's just go through the components of this formula one more time to make sure that we're all on the same page. We have the current that is flowing out of the capacitor in this case, times the capacitance, which is a measure of how many electrons that capacitor can store at a given voltage. We have a change in voltage, or what the actual change in this capacitor's voltage is going to be, which effectively tells us our supply ripple. And we have the change in time, or the period of time that we're interested in, which in this case is our discharge period. So if we actually start plugging in for that, we get that our total discharge current, which we computed as 65.23 milliamps, is equal to our capacitance, which we said was 470 microfarads, times our supply ripple, or the maximum supply ripple, divided by our discharge period, which we said was going to be a discharge time of 16.67 milliseconds per every one of those discharge cycles. So here we have a simple equation now, which will give us our estimate for our supply ripple. So we need to solve for that delta V, and we'll do that by multiplying both sides by 16.67. We get 16.67 milliseconds times 65.23 milliamps equals our supply voltage, then times 470 microfarads. We can divide both sides by 470 microfarads if we want to, and that gives us the supply ripple alone, Now, we are going to have to do just a little bit of basic algebra. You could do this on a calculator, but I think it's a good exercise to actually go and do this out. And it's important to make sure that we're comparing all our units to make sure that everything actually winds up being sane in the end. So we wind up with a milli times a milli, which gives us a micro, right? If we have a milliamp, it's a microamp, right? It's a thousandth of an amp. So for example, a milli times a milli here gives us 1 micro. We have a micro on the top and a micro on the bottom, so they cancel out. And we wind up with 16.67 seconds times 65.23 amps divided by 470 farads. And if we solve that, which I won't do on the screen, you'll actually wind up with a final delta V of 2.31 second amps per divided by farads, which is volts. So we have 2.31 volts of total supply ripple, which seems like it's a really big chunk of supply ripple. It's not incredibly huge compared to 15 volts, but it's still not the kind of thing that we'd want to casually throw around. So unless we had some piece of circuitry that was able to operate with a huge supply ripple, this probably actually wouldn't be a great rectifier. And that's going to imply that we want to increase the size of this capacitor here. Alright, so in our second worked example, we've actually taken the circuit from the first problem and replaced its half-wave rectifier with the full-wave rectifier, which happens to be our bridge rectifier, because it's drawn in that nice little bridge configuration. And what we want to know is, how does replacing this rectifier change our supply ripple estimation? So what we'll actually do is we'll repeat the whole estimation section of that previous problem with a few changes to compensate for our new circuit. Now we know that when current flows, let's say in this direction, it has to pass not just through the load, but through 2 diodes. So not just one diode and the load, but now 2 diodes. And what that's going to do is it's actually going to reduce our maximum rectifier output, the maximum voltage delivered to that load, from the 14.35 volts we had, so which was Vin minus our forward voltage, to now we have 2 diode drops. So our Vmax is actually that maximum input voltage, which we said was 15 volts, minus 650 millivolts times 2. And so in our new circuit, our new Vmax is going to be equal to 13.7 volts. And this new Vmax gives us a new Imax, which is equal to the maximum voltage divided by our minimum resistance, as we did in the previous problem, which is equal to 13.7 volts divided by 220 ohms, which gives us 60.9 milliamps of current maximum. We also know that the time that it's going to take for this capacitor to discharge, or the time for which this capacitor must provide current to the load, is now halved. So instead of using a full cycle of 16 2/3 milliseconds as our discharge time, we are going to use approximately half that, right? So we said it was approximately 16 2/3, so now we'll use exactly half of that approximation before, because now we're using the full wave rectifier, and that means that the total time from discharge to that charge start again, instead of having this shape, right, where we had a DC pulse and then half the time off, we now have a DC pulse followed by a DC pulse. So the total discharge time, the total cycle length, has been halved. So instead of using a discharge time of 16 2/3 milliseconds, we're actually going to use 8 1/3 milliseconds, which is half of that. And then we can plug into our the same kind of approximation we made last time, and now we get that the discharge current of 60.9 milliamps is equal to the capacitance of 470 microfarads times our supply ripple divided by the duration of that capacitor discharge, which we now said is 8.34 approximately milliseconds. And remember, this just came from the fact that we were saying the average current, which we know is 60.9 milliamps, is equal to the capacitance times the change in voltage over the period of time that we're looking for. So we plug in here, and then we can actually solve for delta V. I'm a little bit running out of space, so I'm going to write this over here. And we get that delta V is equal to 60.9 milliamps times 8.34 milliseconds divided by 470 microfarads. And so if we perform out this computation, we actually wind up with a supply ripple of 1.08 volts. Now, if we want it to be really, really quick and make a really, really simple estimation for this one, what we could do is we could try to take the 2.31 volts that we got from the last problem and divide it kind of cleanly in half. So that would have given us a very quick approximation of approximately 1.15 volts of supply ripple, which is an acceptable approximation. We're just making even less accurate of an approximation, and since we're still being kind of pessimistic, since we're still kind of computing a worst case scenario, this would have been a fine, quick estimation for the supply ripple. We spent a little bit more time, did a little bit more detail, and got 1.08 volts. So we know that the supply ripple is going to be less than the 1.08 volt pessimistic approximation that we've made. Of course, there's nothing stopping me from being more detailed in my approximation. If I wanted to, I could actually figure out what the equation is for the capacitor's voltage with respect to time in an RC circuit, which is actually fairly easy to derive. I'm not going to derive that here. I know that the capacitor's voltage is equal to the initial voltage of that capacitor times e to the negative t over the time constant, which is R times C. And if I were actually to plug into that circuit, I would find that after one of our discharge periods, or after 8.34 milliseconds, I wind up with a load voltage of 12.6384 volts. And if I then converted that to a difference from, if I actually subtract that from my initial value of 13.7 volts to find the difference, I would find that the supply ripple was 1.06 volts. So if you look at the difference here, our approximation really wasn't off by all that much in this case. So we actually did quite a bit more work to get just that little bit more detail. Alright, so finally let's tie up that last little hanging thread from that first problem. We said that the supply ripple that we were going to have in that first problem with our 470 microfarad capacitor. Alright, so now we're going to sweep back around and pick up that thread we kind of mentioned in that first problem. Remember, we looked at this particular circuit here with an output filter capacitor that was 470 microfarads, and we found that we were having a rather ghastly figure of approximately 2.31 volts of ripple on that supply output. And we hinted at the fact that if we wanted to decrease that supply ripple to something manageable, a good way to do that would be to increase the size of this filter capacitor. Now, suppose in this case I either went and consulted some other specification, I took a look at this output system, I did some more research effectively, and I found that in order to have efficient operation of this system, or to have the system work well, I wanted the supply ripple to be less than 5% of the target output voltage. And I'm going to assume that the target output voltage is approximately 15 volts. Right? And then any diode losses we have are not really considered into that target output voltage. If you wanted to, you could use the 14.35 figure here. Either would work, but what we actually wind up finding is that our target output voltage times 5% gives us a maximum supply ripple of 750 millivolts if we assume our target output voltage was 15 volts. So we're saying here we can tolerate at absolute maximum 750 millivolts of supply ripple, and we can effectively do all the same calculations that we did that first time in reverse to figure out what the desired capacitance is. So instead of trying to figure out what our change in voltage would be, our supply ripple is, now we know our supply ripple maximum can be 750 millivolts, and we're going to try to solve for our capacitance. And so we wind up seeing that, just like before, we said that the average current is equal to the capacitance times our supply ripple over the discharge period, right, which just comes from our understanding of capacitors. And so if we want to solve for that capacitance, what we're going to be solving for is effectively we multiply both sides by the time period. We get the average current times the time period equals the supply ripple times the capacitance. And if we divide both sides by the supply ripple, we get that our capacitance is equal to our average current times the time interval over our desired supply ripple. And that all that together gives us the capacitance we'll need for that particular value. Let's go ahead and solve for that capacitance. So we know that the average current we got in the first part was 65.23 milliamps. We know that the discharge period, since this is still our half-wave rectifier, is 16 2/3 or 16.67 approximately milliseconds. And our supply ripple, we said, should be 750 millivolts. Okay, and if we solve this equation, we know that a milli and a milli cancel out, and we wind up with 65.23 milliamps times 16.67 seconds divided by 750 volts. If we plug that into a calculator, we actually find up with a value of 1.449, and we still have a milli left over, so milliamps seconds divided by volts, and that gives us a farad. So we wind up with a capacitance of 1.449 millifarads. Now, if you haven't done much work with power supplies, you might actually be kind of surprised to see such a large capacitance. Typically, when we're working with small circuits, we're not working with bulk pools of charge storage, we're working with things like picofarads or nanofarads or microfarads, and probably the most typical capacitance values are in terms of microfarads or fractions of microfarads. Here we have a whole 1.5 approximately millifarads. And you can get these capacitors. You can buy them in singles. They're about 50 cents for capacitors like this. If you're looking for something that has 15 volt voltage rating, like we're going to be applying to it, I actually searched DigiKey and I was able to find components that met our requirements in this case for about 50 cents cheapest in singles and about 15 cents if you're buying thousands and thousands of them. Now that may not seem like a ridiculous price, but keep in mind that at quantity, a lot of smaller capacitors are fractions of cents. So we already have significantly more expensive capacitors, and the capacitors that we're spending all this money on are going to be they're going to have a lot worse non-ideal properties than our smaller capacitors would. So it's generally preferred to be able to use a smaller capacitor over one that is this large. But they do sell these for applications like this. Probably if we were implementing something like this, the circuit from the second problem would probably be something more in line with what we would be looking for. So we'd probably use a bridge rectifier. This is a very common rectifier topology, and we probably, instead of using 470 microfarads, we might take that specification and say, okay, now we want there to be only 5% ripple, and so we might actually figure out in this particular circuit what the supply ripple should be, we might figure out in this given circuit what the capacitor should be to give us that supply ripple. What I suggest you do, actually on your own, figure out a capacitor value for this particular circuit. So kind of retrace our footsteps and figure out what the capacitance of this filter cap should be in this circuit to give us that 750 millivolts of supply ripple that we wanted from the previous problem. a good way to check out all of these and to test how good these approximations are is actually to go and build these circuits in LT-Spice. And you can actually choose real diodes, the diodes in your kit that start with 1N4001. You have a 1N4007, I believe, in your kit. Those diodes are meant for building rectifiers. So go ahead, find their models. They are in the LT-Spice libraries that we've provided. So actually, if you go in and build these circuits and simulate them, you'll be able to see how well we did with our approximations in these worked examples, and you'll actually be able to judge for yourself whether it's worth approximating these kinds of things.